Hello everyone. In this session, we will be learning about fundamental logic gates, which are the building blocks of any digital circuit design. So, the most important fundamental blocks that we have to use in a digital circuit are some of them: NOT, AND, NAND, OR, NOR, exclusive or XOR, exclusive NOR or XNOR. That's a mouthful of names, but don't worry, we will see each of them. Let's look at the NOT gate, or also called the inverter. So from here, from the gates option, I have taken this inverter, as you can see over here. This is my input, and I try to see the output from the LED. So as the name suggests, a NOT gate or an inverter gives an output that is opposite to the input. So when the input is 0, the output is 1, and when the output is 1, the input is 0, which is indicated by the on or off state of the LED. As you can see, this is this table that verifies the functionality of any logic gate is called a truth table. Over here you see this is the input column and this is the output column. So for the input equals to 0, as we saw over here, the output was a high state or a 1, which is being shown over here. Similarly, for a input that is 1, the LED does not glow, which means the output is 0, as verified over here. Now let's look into the next gate, which is the AND gate. Okay, so I'm not doing the AND gate since it was covered in the previous video. Let's look into the OR gate. So I take the inputs over here and I connect them. And I look at the output through the LED. Alright, so let's see the behavior. When both the outputs are 0, the LED doesn't glow. That means output is 0. The moment I switch one of them to 1, the LED glows. That means the output is 1 for 0 and OR of 1. 0 or 1. 1 or 0 still gives me a 1. 1 or 1 gives me a 1. So you can see over here, for the OR gate, when either of the inputs are 1, that very moment my output turns out to be 1. So the only case when the output of an OR gate can be 0 is when all the inputs are 0. Alright, now let's look into the XOR or the exclusive OR gate. This is a bit interesting, and I would like you to give a bit more attention to this gate. Alright, so I connect the LED over here. When both the inputs are 0, the LED doesn't glow. When one of them is 1, the zeros or 1, the LED starts glowing. The other case, when 1 is XORed with 0, I still get a glowing LED. And when both the inputs are 1, you see, suddenly the LED glows to 0. The LED doesn't glow actually. So what does this suggest? If you look at the truth table of the exclusive OR gate, you see that when both the inputs A and B are equal, the output is 0. That means it doesn't glow. When 0 and 0, when A and B are 0, that means both of them are same, I get the 0 output. When both of them are 1, I still get F equals to 0. The only cases when I get 1 is when both the inputs are different, exclusive. When 0 is A and B is 1, then the output is 1. and vice versa. A being 1 and B being 0 gives me 1. So exclusive OR is used to test whether or not two bits are equal or unequal. If the two bits are unequal, as you can see over here, the output of the circuit is high. Alright. Now there's a corresponding circuit which behaves the opposite way. It's called the exclusive NOR or XNOR. So I once again take in two inputs. And connect it to the LED over here. Now look at this. The moment I put both the inputs as 0, the LED starts glowing. Okay. Now let's look at these two together. When I keep one of them 1, 0 and 1, then the exclusive NOR remains off, and as explained earlier, the exclusive OR or XOR gate remains on. Even if I flip it now 1 0, the exclusive OR checks that both the bits are unequal, so it remains OR on. And for the exclusive NOR gate, both the bits are unequal and this remains off. Now when both the bits are 1, you see that the exclusive OR gate remains 0 and the exclusive NOR gate remains 1. Now what does that mean? It means that the exclusive NOR gate remains on when both the bits are equal. As you can see, 1 and 1 they are equal, or 0 and 0 they are equal. In these cases the output is high, and when the bits are not equal, then the output is off. So what does that mean? As you can see, this means that the behavior of the XNOR gate is the inverse or not of the XOR. What do I mean by that? If you look into the, let me zoom this out a bit. If you look into the truth tables of the XOR and XNOR, so this is the XOR which has 0 1 1 0 pattern, and the output for the XNOR is 1 0 0 1. Doesn't this suggest that the XNOR's output is inverse of the exclusive OR gate? Let's verify that. How would we verify? I will try to put an inverter in front of this XOR gate and see whether or not this is satisfied. So I take another inverter over here, and now I set the output. Okay, now you see when it's 0 0, both the outputs match. 0 1, the outputs match. 1 1, both the outputs are matching, and the 1 0, both the outputs still match. That means the exclusive OR gate is the inverse or the not of the exclusive OR gate. XOR gate or the exclusive OR is the inverse or not of the exclusive NOR gate. Now there are similar versions for the AND and NOR OR gate. So for example, you can see the OR gate over here. Now there is something called the NOR gate. These are my inputs to the NOR gate. And so as you can see very well, the OR gate is 0 only when all the inputs are 0. So what do I expect a NOR gate to behave like? A NOR gate will give me 1 when all the inputs are 0, as you can see. So when I give 0 1, this remains off. When I give 1 0, this NOR gate gives an output 0, and when I keep it 1 1, this one gives an output 0. So you can very well see over here that the OR gate which gives me an output pattern of 0 1 1 1. The NOR gate gives me an inverse pattern, or the inverted pattern 1 0 0 0. So that means that if you place an inverter in front of the OR gate, it will behave like a NAND gate. Let me show this once again for the sake of clarity. You can see 1 1 gives the same output, 0 0 gives the same output, 0 1 is off, 1 0 is off. So NOR is the inverse of OR. I can do the similar thing for the AND gate as well. So the AND gate and the NAND gate. Let me choose two inputs. Both the inputs a single input can actually drive multiple gates. Okay, so what is the functionality of an AND gate? As I mentioned earlier, AND gate gives a 1 only when all the inputs to the AND gate are 1. So what do you expect for an AND gate? When all the inputs are 1, only in that case the output of the NAND gate would be 0. So as you can see over here, when it's 0 0, this NAND gate remains on. When it's 0 1, the NAND gate still remains on. When it's 1 0, the NAND gate remains on and the AND gate remains off. And when it's 1 1, only in this case the NAND gate becomes off. And this you can once again verify from the pattern over here. The AND gate gives a 0 0 0 1 pattern, and the NAND gate gives a 1 1 1 0 pattern. So a NAND gate is simply an AND gate for, in front of which you keep a NOT gate or an inverter. In other words, if I put the NOT gate in front of this AND gate, for all the cases the outputs will match.